All right, and we're live.
Hey everyone, welcome to the Stanford MLSys seminar series. I'm back. This is Karan. I'm here with Dan, Fyodor, Piero, and our guest for today, Travis Addair from Uber. So like always, we're gonna have Travis give us a talk for 30 minutes, followed by a podcast style discussion where you, the live audience, can ask questions in the YouTube live chat. Feel free to keep asking questions as Travis is talking. We'll keep track of all those questions and kind of communicate those to him during the podcast discussion. So Travis is going to be talking to us a little bit today about Horovod and how deep learning has evolved and the ability to handle training at scale. So we're very excited. Travis is a software engineer at Uber. He leads the deep learning training team. He's part of the Michelangelo machine learning platform at Uber, and he's the lead maintainer for the Horovod open source project. So who better to talk about Horovod than him? He is going to talk about scaling deep models with Horovod and hopefully some interesting questions and challenges around scaling in general, especially if you're in industry. I think this talk might be interesting to you as well. So Travis, take it away.
Thank you. And thanks everyone for attending this presentation. Let me quickly present here so that we can avoid spoilers. All right. So in this talk, I'm going to be talking about Horovod, as mentioned, which is an open source project that was originally developed at Uber and is now part of the Linux Foundation's AI and Data Foundation, where we've recently graduated within that group. As mentioned, I specifically am the lead maintainer for the project. I also lead a team at Uber called the Deep Learning Training Team. And as part of that, we primarily focus on this problem of scaling up deep learning training, getting these models into production, and being able to retrain them on fresh data in a very efficient way, and making sure that everything kind of works seamlessly end to end so that we minimize the amount of friction between research and production. And so as part of that, lots of things have evolved over the years. Since when Horovod started, we were in kind of a place where most of the deep learning that was going on was primarily research. It came out of the ATG self-driving car division originally. They had issues where their models were taking many weeks in some cases to train. And so Horovod was fundamentally originally about how do we just make this training go much faster by taking advantage of multiple machines, multiple GPUs. And over time, we've evolved the concept of the project, as well as what we do on the deep learning training team, to also be about kind of the end-to-end as well of how does deep learning fit into the entire machine learning lifecycle as we increasingly see more and more machine learning workloads move away from kind of like tabular-based models to more deep learning style models. And so that's what I'll be talking about in this talk. It's kind of like how that progression happened, as well as kind of where things are going looking forward. All right, so first let's talk about distributed deep learning in terms of, what exactly is the problem and what are we solving here? So I always like to start conversations about Horovod with a simple kind of deep learning refresher like this, just to make sure we're all on the same page. So hopefully this isn't like new to anyone, but just to make sure that we're on the same page here, that with deep learning, we're talking about these networks that have many, many layers. You have some data coming in, you might do some light pre-processing like transformation, scaling, et cetera. And then you pass it through these subsequent layers that output a prediction. And then as part of the training process, you compute some gradients that define how you're going to update your model parameters for the next iteration. And this proceeds until you hopefully have a good model, right? And so I like to call out that this diagram in particular is interesting to me because it kind of illustrates some aspects of what makes deep learning different from a lot of machine learning use cases. Specifically, kind of the depth aspect is where we get into things like custom accelerators, things like GPUs, or even more custom ASICs that are coming out of the industry. And so unlike a lot of other problems that were traditionally solved in data engineering, deep learning ends up being a very computationally intensive task. And so we end up needing to think about how we do distributed training, how we do scaling of these systems a bit differently. And historically, there have been two kind of like broad categories of thought in terms of how you do distributed training. The first is what we would call model parallelism, where we take individual layers of the model and think about spreading them across different GPUs. So maybe the first layers, we're going to put them on GPU 0, and then this layer we're going to put on GPU 1, et cetera. And this is really nice when your model parameters themselves are just too big to fit in a single GPU based on how much memory you have on your GPU. But oftentimes what we find is that the biggest problem for a lot of users is not the model size, but the data size, right? And in those cases, data parallelism is what will give you the most bang for your buck. And that's specifically where you take the actual model replica itself and replicate it, or the model architecture itself, replicate it across multiple GPUs. And then what you're doing is you're splitting the data across those instances and training on separate data instances, but with the same model on multiple GPUs. And that's what I'll be talking mostly about today, because that's what Horovod kind of specializes in, but we'll talk a little bit about model parallelism as well. So in the early days, back, when I was at Google back in like 2013 to 2015, parameter servers were pretty much the go-to solution for doing distributed training. We had a system at Google called Disbelief. I think that paper was published back in 2012, something like that, by Jeff Dean. And it was kind of described this kind of parameter server architecture of how we're going to replicate the model, and then the models are going to submit their gradients up to the server. The server will aggregate them, maybe do an average, and then send the final updates back to the models, which will then update their parameters for the next batch, right? And so this is typically done synchronously, where if one of the workers submits their gradients first, and then another worker submits their gradient second, we wait for them all to complete before sending the final update back so that none of the workers get ahead. In practice, you can also do this asynchronously, where you kind of just go wild and let each of the workers kind of update as quickly as they can. But that sometimes leads to convergence problems, as I'll discuss. But this was kind of the earliest solution. And as I mentioned, parameter servers were nice because they're simple. We understand how kind of client-server type architectures work. So they're pretty easy to reason about in terms of fault tolerance and replication and things like that. And like I said, you can also do asynchronous SGD if you want to, where different workers submit updates at different times. But on the downside, when we were trying to take this and apply it to our users at Uber specifically, so at the time it was TensorFlow's parameter servers, the biggest issue that we ran into was usability. So you definitely have can't escape it, a bit of a infrastructure usability issue where you have to think distinctly about how your clients and your servers are going to be spun up in terms of instances on your orchestrator, like whether you're using Kubernetes or whatever. And typically that means that you have to have some kind of DevOps or system administration type person who can tell you what the right resource allocation for each of these instances is. And then you also, in the early days, had some API challenges as well. So there were API concepts that you had to understand in order to know how am I going to distribute my parameters, like from my client to the server, and what aspect of the model workflow is the server going to manage versus the client. And it made things very difficult for users who just wanted to take the code that they had written to run on their local machine and scale it up. And specifically on the scalability side as well, there were challenges too. So by introducing these parameter servers, you're introducing extra hops in the flow of and the amount of messages that you're passing, right? So instead of just sending messages directly to other workers, you're having to go through this intermediary, which is the parameter server, and that increases the total amount of bandwidth utilization when you're doing the training. And then finally, while async SGD is a very nice benefit, the downside, of course, is that because you're letting different replicas proceed at different rates, oftentimes this leads to convergence. Very famous problem is the stale gradient problem, where a worker might have be let's say 10 batches behind or something like that and submit its update, and then suddenly is actually doing more harm than good. So async SGD in practice tends not to be as popular as synchronous SGD, although there are some cases where it's still applied. All right, so what does Horovod do if it's not doing parameter servers then? So the idea behind Horovod is kind of rooted in high performance computing, and specifically a concept called all reduce. And if you go back to some work that was done in this paper here, bandwidth optimal all reduced algorithms for cluster workstations. That was one of the first occurrences where this kind of realization was noted, but it became very popular in a blog post published by Baidu back in 2017, where they specifically talked about this ring all reduced algorithm being the bandwidth optimal way to do this kind of gradient aggregation. And so then the Horovod project kind of spun out of that realization, and the result was an implementation in the open source of the ring all reduce using with bindings for TensorFlow at the time, and then later PyTorch and MXNet. And so this is where Horovod comes into the picture. So Horovod, I think there was a question earlier about where the name came from, so quickly to comment on that one. So Horovod is a Russian word. It comes from a dance where kind of the participants hold hands and sort of move in a circle. So very reminiscent of the ring all reduced, so cute play on words. And the project these days is part of the Linux Foundation, as I mentioned. It supports TensorFlow, Keras, PyTorch, Apache MXNet, and TensorFlow versions 1 and 2 we support. And what really makes it stand out in a lot of ways is the ease of use, being just 5 lines of Python code to have it to get it working, as opposed to having to make major changes to your script, and the high performance features that come from this sort of all reduced technique. So NVIDIA has its Nickel library, which allows you to take advantage of GPU direct memory access, so that you're not having to constantly be taking memory from GPUs, putting in host memory, sending it over the network, sticking it back on the GPU. Similarly, if you're using MPI, you can take advantage of RDMA if you have that infrastructure set up in your cluster. And one of the more novel things that Horovod introduced was also this concept of tensor fusion, where instead of having every single gradient that you want to aggregate being a separate call to Nickel or to MPI, you can batch them together to reduce the number of network calls that you're making to speed things up. And it's very simple to install, just pip install Horovod, and that's all it takes. So Horovod is very performant, scales very nicely up to hundreds of GPUs in our experience, particularly when you're taking advantage of RDMA. These benchmarks in particular are on kind of image processing tasks, but we've also seen similar performance for language models as well as tabular models. And I think one of the most interesting external use cases of Horovod was at Oak Ridge National Lab. So they have the Summit supercomputer, the world's largest supercomputer with over 27,000 Volta GPUs. And the work that they did there that led to winning the Gordon Bell Prize for exascale deep learning for climate analytics achieved over 90% scaling efficiency, which was quite impressive at that scale. And one that specifically broke what they called the exa-op barrier, so 1.13 exaflops peak performance. And Josh Romero here, who is part of that team from NVIDIA, is one of our core Horovod contributors and has done a lot of work to improve Horovod to kind of reach those scaling efficiency milestones. So let's talk a little bit about how Horovod works under the hood. So one of the most important concepts in Horovod is this idea of GPU pinning. So the way that it works is that you have some driver application like MPI run or Horovod run, which we wrote. And then every Horovod worker is going to affinitize itself to a particular GPU, right? So you spin up typically however many workers, you spin up an equivalent number of workers to how many GPUs you have typically. And the reason why you do this is that you don't want to have any contention in terms of the resource usage, right? So if one process is using one GPU and the other process tries to use the same GPU, bad things can happen, can slow things down, maybe even get like some bad memory access. So having this division helps get the performance where we want to be. And so, this is pretty easy to achieve in most frameworks. This is a TensorFlow 1.0 example where we just say, make the visible devices equal to exactly the local rank, where here the local rank corresponds to the local GPU because you're running an equivalent number of processes per host as you have GPUs per host, right? Another core concept is state synchronization. So In Horovod, we expect that all the model replicas across all the workers should have the same parameters, ideally at every point in time, right? And if you don't do this, you end up in a situation like this where worker A computes a gradient and it goes towards the local optima. Worker B computes a gradient, it goes towards the local optima. But when you average their gradients together, they end up going off in some bad direction, right? So if you make sure that the states that every worker is initialized to the same point and then there's no drift, then ideally they should all move in the right direction. And that's what this API call here achieves in Keras. And one other core concept is learning rate scaling. So something a lot of people don't realize initially when they start doing distributed training is that data parallelism means you're training with a bigger batch size. And specifically, your total batch size is basically equal to whatever your local batch size is times the number of workers that you're using to train. And so to compensate for this, we recommend in most cases scaling your learning rate by the number of workers that you're using to kind of like proportionally scale it up. But at very large scales, what often ends up happening is that convergence can be a problem. And so there are techniques that you can use to mitigate this, like one that we call learning rate warm-up, where we just smoothly ramp up the learning rate over some number of epochs before reaching our target one, and then use standard learning rate decay over time after that. And here's how you do this with the Horovod API, just scale by Horovod size and then wrap it in our distributed optimizer. And here's a full example. I won't go into the details too much, but just should be hopefully be pretty clear that there's just some pretty light augmentation of the existing script. We pin the GPU, we wrap the optimizer, and we add this callback, and that's pretty much it. Now, in terms of the Horovod architecture under the hood, what we do is we implement custom operations for every framework that we support. So this means that when you pip install Horovod, you're actually compiling C++ source code that's linked against the native libraries of the framework itself. And so when a framework gets an operation like do an all reduce, which is a Horovod custom op, what happens is that we submit this to a queue internally within Horovod. And then what we have is this control plane that will periodically check the queue, perform what's called a negotiation step to try to figure out which workers have which tensors ready at any point in time, because remember that frameworks like TensorFlow are asynchronous, and so different tensors might come in at different times. Then we do the fusion operation that I mentioned before, where we try to batch them together into a single buffer. And then the worker 0, arbitrarily chosen, will broadcast the final list of operations to all the other workers, and then submit it to the data plane. So in the data plane, we do a simple mem copy into the fusion buffer. We scale it before and after doing the operation in case there's any, to prevent things like overflow and underflow from happening. And then we do the all reduce itself, which is usually implemented by Nickel on GPU, but also 1CCL if you're using Intel, or MPI or Glue are also supported. And so these green boxes here have been where a lot of the optimization has been done by Josh at NVIDIA. So specifically for negotiation, there's a bit vector cache that was introduced to reduce the amount of messages that need to be passed for every control plane step. And in the broadcast, in the fusion step, we used to have a policy of just kind of greedily fusing tensors as they came in. So we'll try to pack the buffers as much as we can. But recently there is some additional work on what we call tensor groups, where you can kind of define which tensors fuse with which other tensors based on kind of like past experience with which tensors come in at which times, which leads to much better performance in practice. All right, so that is what Horovod does kind of in the research sense, but let's also talk about how deep learning fits into the bigger picture of machine learning workflows. So at companies like Uber and others, what often ends up being the case is that training is just one part of the picture, and that you also have other things that go into your system, like you have data you're reading from a data lake, you do some ETL, you maybe have a feature store, a label store, the output goes into a model store, and then you serve this model for real-time prediction, and then maybe also have a model store that you can use for batch prediction as well. And so what this means is that we're not just concerned with deep learning in isolation, we also have to think about the data processing, the feature engineering aspect, and how we actually deploy this pipeline so that it can be used for prediction and not just training. And so in practice, what happens is that Spark is a really common framework that gets used in this world. And so Horovod on Spark was one of the first such integrations that we did to kind of bring deep learning to the rest of the machine learning workflow ecosystem. And the way that it's implemented, the API looks very similar to a typical Spark UDF. We have Horovod Spark run, you pass in a custom function. That function will typically be the equivalent of your training script. And then it returns a result for every one of the workers that you can then do whatever you want with. So you can like save a model kind of persistently within your training function, or even return the model back to the client, to the Spark driver when you're done with the training. But we also wanted to provide a higher level API than this. And so we introduced what's called Horovod Spark Estimators. With this API, what you can do is you can build what you would call a Spark MLlib pipeline, which might have some steps like, I want to normalize my variables. I want to maybe do some indexing of some kind, replacing strings with integers, et cetera. And then as a downstream step, you want to actually do the deep learning training itself. And so that's where this Horovod Spark estimator fits in, is you just define your model, pass it into the estimator, and then the data frame will get passed directly to the Spark estimator, and training will occur on that. And how this works in practice is that, particularly if you're using Spark 3.0, you can now kind of seamlessly transition between doing CPU feature engineering and GPU training. But what we do under the hood is we actually materialize your Spark data frame into a file on HDFS, a Parquet file, and then do the training from there. And the reason why we do it this way instead of using the RDD that's already been, that's backing the data frame itself, is that for deep learning, it's really important that we shuffle the data quite a bit, have fast random access as much as possible. And RDDs tend not to be particularly great for these kinds of tasks. They're, Spark is specifically focused on kind of data flow and, processing large amounts of data. In our case, we're mostly kind of focusing on compute, and we want to be able to just access random pieces of data as quickly as possible. So it turned out for us that using something like Parquet ended up being better suited to this particular task. And so we typically at Uber, and for our Spark Estimator framework, we've used this library that has been written by the self-driving car group at Uber, now open source, called Petastorm, which will read these row groups from HDFS or from any file system. We have support for S3 and Databricks file system, as well as others. And then the Petastorm worker running within the Horovod worker process will do the work of unbatching this row group into individual elements, inserting them into a buffer that then gets shuffled, and then the downstream consumer that's requesting a batch will sample from this buffer in order to generate individual batches for training. And so the nice thing about this approach is that Petastorm can optimize a lot of this data reading process to do caching and buffering, et cetera, prefetching, without having to be kind of bound by the IO aspect. Because again, in our case, we're assuming we're not IO bound, we're compute bound. We're assuming that the network overhead of things like Horovod and the compute overhead of things like the GPU forward and backward passes are going to be kind of the lion's share of the cost. And more recently, we've also been doing integrations with the Ray project. So Horovod on Ray has been one of our big areas of investment recently. And to sort of talk about the motivation here, so with Spark, it's really nice. Horovod and Spark is really nice if you're already using the Spark ecosystem for other aspects of your workflow, and you just want to put training into an existing Spark workflow. But a lot of people are not in that situation. A lot of people, maybe many people in the audience too, initially have their data running locally, their training system running locally on like a single machine, right? They might be using pandas for doing pre-processing of the data. They might be using TensorFlow for training and then evaluation. And then they might write their model to like the model storage is maybe like a file on their disk or something like that, right? And so if you were to ask someone to take this script and make it work at scale in production, that's retrainable, that's resilient, et cetera, what you would usually end up with is something like this, where you maybe have like a Spark cluster, Spark application that you're going to use to do the pre-processing. You might use Horovod to do the training, might have a different Spark application with different resource requirements doing the evaluation, and sort of have multiple like kind of intermediate data sets that sit in between all of these stages. And then because we're using heterogeneous architecture or infrastructure between each of these steps, we need to stitch them together somehow using a system like maybe Airflow to orchestrate everything. And so what you end up with is you have many, many different like files that you're writing that are just kind of like lots and lots of infrastructure glue code written on top of your existing training code. And this ends up being a pretty big barrier to getting models in production, we've observed, is that when a data scientist writes a model, there's very frequently a very long period of kind of engineering effort that needs to be done in order to then get things into production. And so what we like about systems like Ray is that they bring all of this, what would normally be heterogeneous compute, into kind of a single infrastructure layer that's abstracted from you. So for example, if our user in the previous scenario was like using pandas for doing pre-processing and wanting to use TensorFlow for doing training, with something like Ray, they can switch over to Dask for pre-processing, which exposes the same API as pandas for the most part, and Horovod for training, and then have it execute seamlessly on a distributed compute cluster with Ray without having to make very many, if any, changes to their code. And the nice thing about Ray as well is that you can run it locally and it performs just the same, right? So this has been a really big area of interest for us. And taking this a step further, we've also integrated Horovod with RayTune, the hyperparameter search library, so that you can kind of go one step further as well and say, okay, so now I did my training script all in like a single Ray cluster. What if I wanted to run multiple different training trials using different parameterizations of my model? You can do that too, just by adding one additional layer on top of it, like one like file or something like that, without having to make any additional infrastructure investment in terms of like spinning up a new distributed system and keeping track of new state, right? And the API for this is pretty similar to what the Spark API looks like. We have this executor, this Ray executor that takes a training function, looks very similar to the Horovod on Spark execution model. But one thing that I think is pretty cool about Ray that's unique is that we also have a stateful API, because Ray actors can be stateful. So they have this kind of caching layer, this plasma cache that they can use to store things between invocations. And so you could, for example, have a model class that is backed by your Ray executor. And then in a loop on your driver, on your head node, you can execute like a single training step at a time without having to kind of send the state back and forth between the client and the remote worker. You can just have it all live in the remote worker, but be able to interact with it iteratively. And I think that's a pretty powerful thing for doing things like online learning, maybe, or kind of like interactive learning. And finally, I want to talk briefly about Elastic Horovod. So the motivation here is that in a typical scenario, you might have, particularly if you're training on cloud with preemptible instances, you might have a worker fail, a worker come up later in the process, and ideally you want to be able to seamlessly switch off of using the old worker and onto using the new worker, right? So how can you do this? And let me also take a moment to explain why you might want to do this. So obviously fault tolerance is a big one. If a worker dies, new worker comes up, you want to be able to keep training without any interruption. But there's also kind of like cost motivation here as well. So if you're running in cloud, preemptible instances can save you like 70 to 80% the cost of a dedicated instance. And so if you could train all on preemptible instances, which might be taken away from you at any moment, you can save a lot of money, right? Similarly, if you're on-prem, what you see is that you often have a finite number of resources, and ideally you'd like to be able to fully utilize them at all time. So if you're able to scale up and down the number of workers based on the demand, so like, no one's running, I want to run a job, I get all the machines, then some other guy comes in and we tear down the resources and give that person the resources. That's the kind of thing that we have in mind. So these are all scenarios where something like elastic training would be useful. So how does this work under the hood? So the control flow for Horovod, Elastic Horovod looks something like this. We have a driver that usually sits on top of like your Ray head node or your Spark driver. We create the workers, they synchronize their state, they do some training, maybe one of the workers dies. A host is discovered by the driver. The surviving host calls reset, asks the driver to recreate the cluster. It does so, spins up the new worker, they synchronize state and continue training like nothing happened, right? Now you'll notice that there's also this commit step that happens here at the end. This is a pretty costly operation. You're basically having to copy the state so that if a failure happens, you can roll back to the previous state, assuming that maybe there were like some intermediate modifications made that you want to be able to undo, right? However, because this is expensive, we try to avoid calling commit as much as possible. And so we have this alternative way of doing worker removal that we introduced called graceful worker removal. And the basic idea is that if you can get advance notice that a worker is about to be removed before it actually gets shut down, then you can like remove it from the Horovod job without having to do a commit and do a rollback of the state. Because you know that you can remove it at a point where all the workers are in sync and everything is already good. So in this scenario, the workers synchronize state, they train, they do this check for host operations, which is very lightweight. And since a host removal event was sent to the driver, we can notify the workers that a worker is going to be removed, and that can signal them to say, okay, let's stop for a second, remove the worker that's going to be shut down. And then that worker exits before it actually gets terminated by the cluster orchestrator. And so training can continue then without any significant interruption. And in practice, we found that this gave very significant performance benefits because we're avoiding this costly commit operation. And last but not least, I wanted to very briefly comment on my thoughts on some recent trends in distributed deep learning that we're exploring. So the first is what we call hybrid parallelism. So I mentioned at the beginning this idea of model parallelism. So what we're seeing with these very large tabular models in particular is that they often have these very large embedding tables that can't fit on a single GPU. And so what happens is that in this new model that was kind of popularized by Facebook's DLRM, we instead take the embedding tables and kind of place them on individual GPUs. So like one feature might be on one GPU, one feature on another. And then we use this all-to-all operation to take the outputs from those embedding tables and then send parts of them to different workers in kind of a more traditional data parallel fashion, so that in the second half here, each of the workers is only operating on a subset of the data. So in this way, you kind of get the best of both worlds. You can shard your model parameters, and you can also work on very large batch sizes. New accelerators, another one that we're really interested in. So Samba Nova, Habana, Cerebras, GraphCore are some examples of companies that are in this space. I think that it's still pretty early days here, but we're doing a lot of looking into how we can integrate with them, how we can leverage their stuff, both for training as well as inference. Hyperparameter search. So this visualization, I'm not sure if it will click with everybody, but this is what I came up with. So if you bear with me for a second, if every number here is a GPU and every color is a trial, then what we can do is, if you imagine like a population-based sampling strategy where you're like doing maybe successive halving, then what you can do is some number of epochs, like here I chose 10, you take the lowest performing trials, you take them out of the system, you allocate their GPUs to the better performing trials, And you successively do this over and over again until you end up with like one really good trial that you just want to complete as quickly as possible so you can move on with your life. And this is really nice in terms of balancing between this explore exploit kind of like trade-off, right? Where at the beginning you want to focus mostly on exploring different options of different parameterizations of your model. And then as you identify the ones that are succeeding, you want to move more to an exploit model where you're taking the most advantage of the resources you have. Now, why is this particularly relevant to distributed training is that it turns out that when you do distributed training, if there are going to be convergence problems due to having a large batch size, they will show up during the beginning of the training process as opposed to the end of the training process. So what that means is that you start off with a lower total batch size, meaning a lower number of GPUs at the beginning, and over time transition to a higher number of GPUs, a bigger batch size, then the effects on model convergence will not be felt, but you'll be able to train a lot faster. And finally, unified end-to-end infrastructure. So kind of coming back to systems like Ray, I'm really excited about the potential for being able to take the seams out of a lot of these steps. So currently we have very distinct separation between what we do during feature engineering and what we do during training, where we have feature engineering on the left, dumps the data to like some materialized file system. Then we do the training. So what we're seeing is a slow migration, a slow convergence between these different steps where, in the future, we're hoping that we can do things like co-locate our training nodes with our pre-processing nodes, be able to directly access the process data in memory, maybe even using shared memory, right? As opposed to having to dump it to disk. And through this, dramatically speed up the end-to-end workflow. And that's it. A little bit over time, but hopefully there'll be enough time for questions. Please feel free to ask any, and thank you very much.
Awesome. Thank you so much. Really enjoyed the talk. Yeah, I want to, like Travis said, remind the audience, feel free to ask questions and we'll get those across to Travis. So just to kick us off, I guess, one question that I was curious about was, I think Horovod did a great job of putting sort of a really nice wrapper around bring all, reduce, and distribute data like parallelism. Do you have thoughts on model parallelism and data parallelism more generally? And so like more recently, there's been a lot of work on like pre-training with self-supervision, and a lot of those models actually are too large to fit on a single GPU, right? Even the largest GPU can't fit like GPT-3. So do you have thoughts on just how that interaction takes place? And I think it's connected to one of the questions somebody in the audience asked, which is, are there rules of thumb where like Horovod becomes more useful, less useful, and how does that interact with model size, data size, things like that?
Yeah, that's a good question. So to the first question about model parallelism in general, I would say that this is probably the area I'm most interested in right now. I think going back to last year, we saw a really great paper from Microsoft on this zero optimizer. And there have been a number of really cool implementations of that since then, like Fairscale from Facebook. And I think that this is a really promising direction that we're starting to invest more in with Horovod as well, particularly because we have these large like tabular models, for example, with these that need to be kind of like sharded in this way. And so, yeah, absolutely. I think this has been a promise for a very long time, and it's still early days. Like I remember back to a TensorFlow Dev Summit, I think it was a couple of years ago, there was this TensorFlow mesh library that was done, which is kind of like along the same veins, right? It's like, let's combine model parallelism and data parallelism. But I think we're finally starting to see it become like a production scenario. And I think right now, one of the big like kind of open questions there is really like, okay, so we train this model that's too big to fit on a single GPU. Now, how do we like efficiently serve this like in a cost-effective way? And I think that's one of the next kind of like areas that people will be looking at. But yeah, I think that that's a very promising direction. And then in terms of best practices for when Horovod works well and when it doesn't, I would say that Horovod will work well in probably most scenarios, but there will always be caveats. And one of the biggest caveats is that you really have to get aware of how you manage your learning rate in a distributed setting. So, and I think right now there's no good like rules that you can use other than like doing some experimentation, like hyperparameter search, in order to find learning rates that work well. But definitely as a starting point, as I mentioned, scaling the learning rate linearly by the number of workers is a pretty common practice. Using warm up and using learning rate scheduling is very common when you get to larger batch sizes. But after that point, if you notice that there's like differences in terms of how your model is converging at a very large batch size versus with a single GPU, then it really becomes more of like a research problem unto itself, right? Of figuring out like how you're going to most effectively tune it. Another thing I would mention is that how you do your partitioning and your shuffling of data ends up being really important. So when you have small data sets, like Horovod is not going to give you any material benefit, right? It's only comes into play when you have very large data sets. And even then you have to be cognizant of how you do shuffling, because sometimes what will happen is that because you're partitioning your data across different workers, you're not getting true kind of uniform sampling of the data, right? And you end up getting some correlation between your samples. And so sometimes we have observed that like models don't converge as nicely because they're not doing enough shuffling of the data. And so thinking really, really hard about like, am I shuffling enough to get good performance here is pretty critical too. And the last thing I'd say on this note is that oftentimes, like when you're thinking about scaling neural networks, your first instinct is to use something like Horovod to distribute it, but it's often not really your bottleneck. And so people will come on GitHub and observe that, I tried Horovod and it's actually slower. And the reason is because, you weren't really bound by the like forward and backward pass of your GPU. You're actually bound by something else, right? Data being a big one. Oftentimes the IO of reading in batches is actually slower than the actual forward and backward pass of your model, in which case you should try to solve that problem first, get a really good data pipeline working. It's often also the case that you're not fully utilizing a single GPU. So if you're looking at NVIDIA SMI and you're not seeing 100% utilization, like for most of the time, then you should probably try to get to that point first and then, move on to distributed training. Only when you're saying like, okay, I'm getting really good utilization of my GPU, and I have a fast network, like for V100s, we would recommend like 100 gigabit per second network as like a good rule of thumb. Any less than 10 gigabit per second, and you're probably not going to get really good results from distributed training. And even then, you'll probably want to use like compression of your gradients, like FP16 or use Apex or something like that, or I'm sorry, AMP. So yeah, that's all to say that definitely make sure that your bottleneck is in your like the time it takes to process data through a single GPU before turning immediately to distributed training.
Travis, let's switch gears a little bit. So I wanted to touch upon one of the points that you discussed about in the future work, in particular the work with Ray and the having heterogeneous compute, and the fact that we can now have a way to obtain machines and allocate machines dynamically that will make it so that you can do elastic training of your models. As we've been working with it, like on this idea together with like the Horovod integration in Ludwig, etc. And this is like kind of the set of things that we're working on towards Ludwig version 0.4. I wanted to give you the opportunity to talk about it if that's something that you want to touch upon.
Yeah, absolutely. So Piero and I, work together on Ludwig, and Horovod has traditionally been the way that we scale Ludwig up. And so what we've been doing, but I mean, to take a step back, one of the issues that we've had with scaling Ludwig in the past has been that, it's not just the kind of going back to the last point, I guess, it's not just the distributed training aspect. There's also the data transformation and data reading aspect as well that we have to be aware of. And so we've been doing a lot of work recently on making Ludwig be able to perform faster end to end and perform at higher data volumes by doing things like introducing distributed data frames like Dask, by using frameworks like Petastorm so that we can write the data to disk as opposed to having to keep it all in memory on the workers. And so, when we were looking at what technologies we were going to use to do this, Ray was a really compelling one because we had recently done some integration work on Horovod on Ray. And I like that Ray also brings in this whole ecosystem of other technologies you can apply to, that you can kind of like pick almost like from a catalog, right? It's like, okay, I want to try Modin for my data processing. I want to try Dask, and just be able to seamlessly plug that in without having to change your underlying infrastructure. So when we were looking at options that were out there, one option is you kind of like roll your own solution, right? You like maybe use Kubeflow or something like that. And then suddenly you're having to maintain two separate code repositories, one for like Ludwig that is at scale and one for Ludwig that's on your laptop. And we didn't want to go down that route, right? Because that would be prohibitively expensive from like a maintenance standpoint, right? But with Ray, it was very nice to just say, here's this very thin, layer that we just decorate on top that we can use to like seamlessly scale things up to run at very high scale. And we're hoping that over time, these sorts of seams will become even, more seamless, right? Where, the data processing and the training, we just merge them together into kind of one smooth step, as opposed to, today where it's very common practice to write the data out to disk. So that's what we're hoping to achieve with 0.4. And then also, of course, I should mention the hyperparameter search. So Ludwig has hyperparameter search. RayTune is, hyperparameter search built on top of Ray that supports Horovod. So bringing all these things together, you only have one piece of infrastructure that can run kind of all these steps end to end.
Right. And so to like follow up on that, basically we will get into the point where you have like an heterogeneous infrastructure supported by Ray, Horovod scheduling the training, and Ludwig on top figuring out what actually is the workload that it will be allocated to all these things. It seems to me like it's I'm really looking forward to that. So I will be happy to discuss about it later. But that sounds a pretty compelling kind of proposition to me.
Absolutely, yeah.
Hey, Travis. So I was kind of wondering, what were some of the lessons that you found maybe particularly surprising when you were first building Horovod? Particularly interested in anything that, or what was maybe not clear from some of the academic papers or literature from before. I think, like you mentioned early on, it was clear that this idea of the ring all reduced was very influential. But I imagine that paper didn't have all the answers for building out Horovod afterwards.
Yeah, well, I think one of the actual most interesting observations, kind of seeing Horovod in practice, is that while ring all reduce is like the bandwidth optimal, yada yada solution, it's actually not always the best one, and particularly when you're at very high scale, like when you're running on like a supercomputer like Summit or something like that. You actually are not bandwidth bound, you're more latency bound, which is interesting. So like the time it takes to like send a message all through the ring, like, one step at a time, right, becomes like very expensive, right? So what you end up finding is that in practice, we implemented at one point a strategy called hierarchical all reduce, which is more of like our implementation was like you do ring all reduce on a single worker, and then you do like you do cross rank all reduce, and then do like a final round. So it's kind of interesting. But in Nickel now, what they do is they now support a tree-based all reduce, and I think other topologies as well, kind of natively. So we no longer like recommend people use our hierarchical all reduce, but I think that was an interesting kind of early observation, was that sometimes it's not actually the bandwidth that's the main source of problems. Another one was, I think we've done so much, particularly Josh from NVIDIA now, to optimize the control plane of Horovod. And this is kind of, the control plane in a lot of ways is like Horovod's unique contribution, right? Because Nickel does the heavy lifting of actually aggregating the gradients. And the control plane's job is to provide this kind of framework agnostic layer to orchestrate like which gradients are going to be aggregated at a single point in time, and how many gradients are we going to aggregate at once, right? That's the tensor fusion component. And early days, we used kind of simple point-to-point communication that MPI provided for this, where it was like, okay, I'm going to tell worker 0 what tensors I have ready, and then worker 0 is going to collect all this information and tell everyone else, like which tensors are ready, and then proceed from there. But then we realized that this point-to-point communication was not super efficient, and so we implemented it using collective operations, so primarily all gather from MPI. And then we realized that even this was not fast enough at supercomputing scale. So that's where you get this bit vector all reduced cache, where what you essentially do is like every tensor that comes in, it has all this metadata associated with it. It gets assigned to a single bit in a vector. And then over time, like every time a request is made, you just have to do a bitwise AND operation on these vectors across the different workers to see which tensors are available on all the machines at once, right? And then so instead of sending these big payloads, you're sending like a single bit, right? And that actually ended up being hugely impactful for improving the performance. And then finally, the grouped all reduce being the next one really made a huge difference in terms of getting that last additional performance boost. And so at this point, I think we're in a pretty good place with Horovod's performance, but in early days, what works at like 100 GPUs like doesn't really work at 10,000 GPUs, right? And that was what became apparent very quickly.
Yeah, that's so interesting, the way that the algorithms and the system design change based on the constraints. And I think there's some pithy quote somewhere that every time you scale up like 10x, like the whole problem changes.
Right.
Yeah.
I had a kind of follow-up question about Elastic Horovod, which I think is really interesting. So how smooth is that auto scaling where we go from maybe many machines to fewer, or vice versa? Are there like other caveats besides like rescaling the learning rate that someone should be aware of and you guys had to tackle?
Yeah, it's a really good question. And I would say that in some ways, the research is kind of like still open on a lot of this. Our assumption going in was that playing around with the number of workers would have very significant impacts on model convergence. And so far, we have actually not observed that to be the case, at least when you're doing a lot of standard kind of benchmark data sets like CFAR10 or like ImageNet. We do not see this degradation in convergence that we expected and we play around with like different frequencies of like host removal and host add, right? So we say, okay, let's do it like, every minute or every 5 minutes or something like that and see how that affects convergence, right? And so overall, like we haven't observed that. Our assumption is that in some cases, at a minimum, you'll need to do some amount of warm up when the size of your pool changes, right? So if you go from like 4 to 8 workers or something like that, suddenly you just like increased your learning rate if you just kind of apply the standard like linear scaling, right? But in practice, what you probably want to do is do some amount of like some number of batches where you just slowly interpolate to that learning rate before you just jump right into it, right? Similar to what you do at the early phases of training. But again, an interesting observation here is that these effects will be mostly prominent in the earlier epochs of training. So if you can get away with it, doing something like keeping the number of workers consistent or maybe even just low at the beginning, and then scaling up over time and allowing more entropy in the number of workers as you get deeper and deeper in the training process, will reduce the kind of like effects on the model convergence.
That's very interesting.
We actually just had a really great question from the audience, I think, latching onto some of this conversation that we were having about the constraints of your workload affecting your design decisions. So it's a question from Pat B, and it's about, I guess, the deployment of Horovod. Have you seen like deployment mostly in like supercomputer type applications, or usage in like big tech? Or what about even like usage in the corporate world outside of big tech? And I guess a follow-up there, like how do you see the differences in those use cases like affect like how people use it, deploy it, and how you've like built it over the years?
Yeah, it's a great question. So I would say that a lot of our partnerships that we have with other companies So we've had a good working relationship with national labs. So we see a lot of people in the supercomputing community using Horovod. One of the big reasons there is that all of those organizations are very heavy users of MPI, and Horovod was originally written with integration with MPI. So we now have a non-MPI path for people who are not supercomputer users, but for people that are, like, that MPI is very important for them, right? Because it fits into their existing workloads, using, say, Slurm to, like, allocate the resources for their job. But over time, we've definitely been seeing a migration towards more and more like cloud-based orchestration, right? So like using Kubernetes and things like that. So we had an early integration with Kubeflow. It was called the MPI operator. I think in practice, it's really just the Horovod operator. Like it was specifically for Horovod, but theoretically, you can use it for other MPI tasks, I guess. So we do have a lot of people who use Kubernetes specifically. And I think ever since we introduced Horovod on Spark, we've seen a really good adoption of that as well. So we have a good working relationship with Databricks. And so they have a Horovod runner that sits on top of their Databricks platform that a lot of users use. And they also are now using the Horovod Estimator API as well. But one of the things that most excites me about Ray is that it solves these like orchestration problems very elegantly, particularly for Elastic Horovod, because when I was initially kind of like designing Elastic Horovod and implementing it, I was like, man, how exactly are we going to provision this stuff for people, like in a way that is reusable? Because are we going to have to write like a separate autoscaler for like every like orchestration system? Like, how are we going to do this? And so one of our contributors, Enrico from a company called G Research, added really good Elastic Horovod support for Spark. So now that's available. But doing it outside of Spark, like the Ray integration was kind of like the savior there, because Ray already runs on like Kubernetes, AWS, et cetera, has auto scaling built in. So doing Elastic Horovod on Ray ended up being kind of the smoothest way to solve that particular problem for users. And so, our expectation is that we hope to see some, increasing adoption of Ray now that we've added that feature. So Spark took a little bit of time to start ramping up the adoption, and we expect that we'll, over time see that with Ray as well. That's kind of where we think the next big trend will be.
Yeah, I want to just ask you the last question, because we're like 4 minutes off. So I'm curious to get your take on the interaction between a lot of the work that you're doing in software and hardware. I think you mentioned a few companies that you were excited about in terms of just some of the way that they're changing how some of these like workloads are actually handled. So I'm curious if you have thoughts about how to be adaptive to those kind of changes, and where Horovod might fit into that future.
Yeah, that's a great question. So it certainly goes on a case-by-case basis with like the custom accelerators. So things like TPUs or Cerebrus's hardware tend to be like kind of more of self-contained ecosystems, right? It's like the deployment and the parallelization, et cetera, kind of all happens within the chip. Whereas you have others that are taking more of a modular approach, similar to how NVIDIA and AMD have approached GPUs, where you think about like a single unit of compute that then can be kind of like scaled up or down based on your demand needs, right? So Habana would be one that kind of fits more into that model. I think Samba Nova too, if I remember correctly. And so those I think are really good potential like integrations for us of saying, okay, well, if Habana or Samba Nova has an API similar to CUDA, then we can implement a module within Horovod that does the work that we do today, but on top of their hardware, right? And then our users who are running locally on their laptops can then scale up their code the same way without having to make any modifications, right? And so, yeah, we're hopeful that we'll be able to continue working with some of these companies. So we definitely have a lot of contributors to Horovod from Intel that we, work very closely with. And so we're hopeful that they will, continue working with us as the Habana stuff gets further and further along.
Awesome. Yeah, no, I'm very excited to see where Horovod is heading in the future. So yeah, I really want to thank you for taking time out and talking to us and our audience. I want to thank everybody in the audience for attending and asking questions. If you're not subscribed to our mailing list, go to our website, mlsys.stanford.edu, subscribe to the mailing list, subscribe to the channel. And we're going to keep doing talks every week. Next week, we have Josh Tobin, who will talk a little bit about issues around machine learning deployment. And so that might be interesting for folks. He also runs a course that I encourage you to check out. Thanks, everyone. Bye.
Thank you. Bye.